So greetings. In this video I will tell you some things about generalized logic programs. Generalized logic programs. So we are still dealing with the logic programs settings, but soon we will make it to the functional programming paradigm as well. So generalized logic programs. Okay, so again we will have implications. Again we will have a single variable on the right hand side on the implication, and on the left hand side we will have a single conjunction. But this time we are allowed to negate some of the variables in the body of the clause, not in the head but in the body. So a clause now, in a generalized logic program, has form of P1 and P2 and so on and Pn. This is just the same as before. Each Pi is some variable, some say Boolean variable, but you are allowed to negate those guys as well. I would usually just make two clusters, and the first cluster for the positive variables and the second cluster for the negative variables to R. So you are not allowed to negate the head. Again, just like in the classical setting, we have this part as the head of the clause and this part of the body being the body of the clause, and each Pi and each Qj and each R and the R, the singular R, are always members of a fixed variable set Z. So basically it's generalized because you are allowed to negate the members of the body, but of course you cannot negate, say, the conjunction itself. Now, a program is again an arbitrary set of clauses. Program P usually do not have a P, same thing, and set of clauses. And we can bounce into problems with generalized logic programs. So actually giving the semantics of generalized logic programs will be much harder than the canonical semantics of logic programs without negation. So for example, I will go through some examples. So example 1 is just I have three variables P, Q and R and three clauses, like not P and not Q implying R, not P and not R implying Q, and not Q and not R, guess what, implying P. So that's one program. Now the question is, what semantics should we assign, should we associate with this program? And if you just blindly do the same thing, which we've already done, so we will start by the all zero, all false, all zero variable assignment, because that's the least element of the poset of the assignments, and you just run one iteration of the function tp. So the new value of p, in order to compute the new value of p, we should collect all the clauses having p on the right hand side. So there is only one clause, this one here, with p on the right hand side, and we should evaluate the body, which is not q, yeah, that's then the negation of 0 is 1, okay, and not r, which is 1 as well, so 1 and 1 is 1. Hence we should set p to 1. Similarly, we should set Q to 1, and similarly we should set R to 1. Okay, but now if you just move on TP square button, so you just iterate this function once more, then right now we will have, okay, so P is now 1, so not P is 0, and not Q is also 0, meaning the left hand side is 0, so the new value of R, being the supremum of the bodies of the clauses containing R as a head, will be 0, which means that the new value of R is 0. And the new value is for Q and for P is also 0, which means that it just bounces back and forth between the 0 and 1 assignments. So actually it doesn't converge, so it does not say converge, and also it doesn't increase, so it's not monotonic. Monotone. And actually it produces a fixed point, but it doesn't compute a minimal model. So similarly as before, if an assignment is a prefixed point of the function TP, then and only then it is a model of the program. So for example here this guy is a prefixed point because the TP of this is 0, 0, 0, which is smaller than 1, 1, 1, but it's not a minimal model, because if you just considered all the models of these guys, well, it's not that hard to see that this is equivalent to P or Q or R, each of these three clauses. So 111 is a model, and 110 is a model, and 101 is a model, and 011 is also a model of this particular program, and so is this guy and this guy and that guy as well. But this 000 is not a model. So basically in this setting for this particular program we have this guy as the models, set of the models of P. And oh well, you can see that there are 3 minimal elements. 3 minimal elements. And this thing itself is a problem because we want to associate one single model for this program as the semantics of the program, and we also try to minimize the truth values, but who can tell which of these 3 should we choose? So basically there is absolutely no real algorithm which can just pick one of these in favor of the other 2 by using some justification, which means that something is wrong if you want to just consider this 2-valued logic of true and false and try to produce a single minimal model of a program, because, well, you have absolutely no reason to favor one of these minimal models against the other 2. So if you have negation, it seems like, well, the usual 2-valued logic is not really sufficient anymore, and there are more possible solutions to this, but one of them is to use the 4-valued logic. The 4-valued logic. So basically we have the elements of, well, 4 is just 2 times 2. This means that they are pairs, and on each coordinate you will have an element of the poset 2, which means you have the first coordinate set either to 0 and 1, and there is the second coordinate also set either to 0 or 1. Basically, they can be seen as intervals, like I will call them intervals. So the elements of the 4-varied logic are 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so these will be the truth values we will try to assign to variables. Now, what's the meaning of these if you just consider these to be intervals? So, for example, 0, 0, it's a closed interval, contains only the single classical variable, classical bit of 0, so it might be reasonable to call this value to be the false value of the 4-varied logic. For some reason, the experts dealing with this part are preferring a double-paired F to denote false, and similarly it's a double-paired T to denote true. So this is F and false, also called false, T also called true. Okay, so these are just shorthands or other notations for the very same thing. Now 0, 1 is the unknown value, so if you just wonder a bit, well, then you have an interval which contains both 0 and 1, so we don't really know which is the actual value. Let's say this, and this is denoted by a button. It has a reason, and we will see the reason soon, but this is the so-called unknown value. And for the last one, for 1, 0, we just included for the sake of completeness, but it will turn out that our algorithms will never produce this particular value, so this is usually called the tab, and this is called the inconsistent logic value. And this also makes sense, because if you just see this as an interval, then this interval is empty, because there is no logical value which is at least 1 and at the same time is at most 0. So there are no logical values which can satisfy these two conditions which can belong to this interval. Now the other 3 options are called consistent values. So this guy here is the only inconsistent value, and the other 3 guys are consistent values of the 4-varied logic. Now, similarly to the case of the binary logic, there was an ordering of the bits. They were made into a poset, and we can make these 4 values into posets, well, in several ways. And so there will be 2 partial orderings of these 4 values. So there will be 2 partial orders. Over the 4-varied logic, over the values of the 4-varied logic. There will be the truth ordering, which is usually denoted as being less than or equal to the subscript of t, and the other one is the precision ordering. P. Okay, so the truth ordering it means that one interval is more true than the other if both of its endpoints are more true than the corresponding endpoints of the other intervals. So formally xy, this is the interval, and member of 4 is smaller than or equal to xy, x prime, y prime, if, according to the truth ordering, if and only if x is at most as true as x prime and y is also at most as true as y prime. So basically, for example, 0, 0 is less true than 1, 1. Yeah, that's good, because false is less true than true. That's what you already had. And we will see several examples. And the precision ordering makes that, okay, so I have one interval and another is more precise if it's contained completely in the other one. So basically you have more information of the actual value. You can view this as having more information about the actual value. So it means that the interval is contained if and only if, according to the precision ordering, okay, so I have to move the left hand side upwards and the right hand side downwards. So this is the difference. Here y prime should be smaller than y. Okay. Now we can make any poset to a poset of intervals using these two guys. So this is a generic construction. So it's a generic construction. So from any arbitrary poset P with some ordering, we can make these two posets using the very same definitions, the poset of intervals with the two orderings. So we can make okay, so that was the seconded, right? So we can make P times P equipped with, say, the precision ordering, or with this, well, let's call this truth ordering as well, the same way. Yeah, that's great. So let's try to draw this. So for example, for the truth ordering. For the truth ordering, of course, we have 0, 0 sitting in the bottom. And if we just increase one of the coordinates, we will get that 0, 1 is larger than 0, 0, and also 1, 0 is larger than 0, 0, but these two values are not related. And then we will have the 1, 1. So this is the truth ordering. And you can just write the other names if you wish. So this is false, this is true, 0, 1 was the unknown value, and the 1, 0 was the inconsistent value at the top. So this is how they are related according to the truth ordering. This is the ordering we, with respect to which we want to minimize our models. And the other one will be useful because our algorithms will be, so we will be able to prove that our algorithms converge after some steps by studying this precision ordering. So for the precision ordering, the largest interval is on the bottom, so it's always the interval which contains as left hand side the least element of the poset, and as right hand side the largest element of the poset. So it will be 0, 1, because according to this definition, to move upwards you have to push the first value upwards and the second value downwards, or remain in place. So if you just push this upwards, or if you push the second one downwards, then you will end up with these two values, and according to this ordering they are not comparable, and then you just push the other direction to the other side. And this is the reason why this guy here is called bottom and this guy here is called up, because according to the precision ordering They are the least and the greatest element of this small poset. And then we have the true value, and then we have the false value as well. Yeah, now that's good. Also, there are operations on these logic values. For example, we used conjunction for the bodies, and we used disjunction in our formally computing the new value of a variable. And we also have to treat the negations somehow. Now, if you just think a bit, then, well, conjunction and disjunction in this poset here is the same as taking the supremum and infimum if you just look at the classical variables. Because here in this poset, the supremum of true and false is true, and this is the same thing which happened in the classical logic. The supremum of 0 and 1 was 1. So here we have the supremum and the supremum and the infimum operators behaving the same way as the disjunction and the conjunction on the classical coordinates. And for example, if you just want to compute, say, true and the unknown and false, here it is unknown and false, so the infimum of these two values, the greatest lower bound, will be the false value, which is fine also, because if you just make a conjunction of a logical variable which you do not know the value, the exact value, but if you make a conjunction with the false, then you end up with the false definitely. So it makes sense to use, and there are the other examples are fine, which are not involving the inconsistent value, because if you just throw in the inconsistent value, well then everything breaks basically. But conjunction and disjunction are just simply the supremum and the infimum operators of the truth ordering. And in general, if you just want to compute, say, the supremum of some values xi, yi for some index set I, then you just have to compute this infima pointwise. So you just have to compute the conjunction of xi and the conjunction of the yi for each I. Yeah. So you just have to compute these coordinate-wise. And similarly for the supremum as well. So the supremum of the xi, yi's are just the supremum and the supremum. Yeah, so you can check these. So yeah. So for example, just the infimum of these two guys will be 0, 0, which is the same as the infimum of 0, 1 in the first direction and the infimum of 1, 0 on the second direction. So it's on the second coordinate dimension. So it's, as I said, factoring or throwing the inconsistent value into the bunch is, well, it makes things not that intuitive actually. And we have the precision ordering, so well, there we can call the supremum and the infimum to be the supremum and the infimum in this poset, but it's a better choice not to use the supremum and infimum signs in this poset as well, because that can lead into confusions. So we just denote plus in a circle and times in a circle for the supremum here and for the infimum here, just not to confuse the supremum in the two different posets. So for example, true and supremum here false is just the true and false is just the top element, because the supremum of this guy and this guy is just their least upper bound, which is just the top value, for example. But at the same time, if you just use the other supremum, then you will of course get the true. So this is different. That's why we are just using different signs. Now, okay, so we know right now that conjunction and disjunction, in order to be preserved, if you already have true and false values, so you are working with the false and the true values, then that's actually an option for conjunction and disjunction to use the supremo and the infimum operator of the truth ordering. Now, the question is how to handle negation. And well, for negation, it's of course obvious that you want to do this. Negation should make true to false and false to true. Yeah. Question is, what should we do with the other two values? There are many options here, of course. But if you just think about these pairs as intervals, then if you just know that a variable can be either 0 or 1, then the negation of this variable can be also either 0 or 1. So it makes sense to define the negation of the unknown value to be the unknown value as well. And if you cannot really assign any Boolean value to a variable, then you cannot assign a value to the negation of the same variable. So it makes sense that negation should just put the inconsistent element to itself as well. So, for example, if I'm just draw this to this other poset, then I will get this. This is the same, but just the elements are just rotated, so it's not a big deal. So yeah, that's how it works. Negation should just transform the true to false and backwards, and the other two guys are just fixed points of the negation operator. Now you can check that the definition of this negation is just the negation of xy, of the interval xy, is just the interval not y, not x. So this is the algebraic definition of the very same thing. For example, for negation of 0, 0, we will have, okay, so you have to negate this 0 and then negate that 0. Yeah, so that's fine. So negated 0, 0 is 1, 1. Again, negated 1, 1 is just the negation of this second coordinate, which is 0, and the negation of the first coordinate, which is 0. That's fine. So not true is false, not false is true. And I'm just doing for the unknown value for the first dimension, you have to negate the original second dimensional, and then you will just end up with 0, 1. Okay. Now, yeah, that's great. So basically, the negation of true is the unknown value is just the unknown value, and this is how we evaluate the our formulae or our clauses. Now, another question is how we handle the implications, because an implication can be also defined several ways. So when is clause satisfied? Well, and there are again many possible options, and the path we choose is that if head to tail to body to head, sorry. So if we have a close, then the close has some body and a single head. So body to head is satisfied by an assignment U if and only if I'm just evaluating the body and I also evaluate the head, and there is a relation less than equal to according to the truth ordering. So right now of U, and the assignment of U is just a number of 4 to this head. This means that we just assign a value from 4, so basically an interval for each variable, and then we just evaluate the body of a clause, which is just a conjunction. We know how to do this, of variables. Yeah, they are given by you, their value, and the negated version of the variables, which also already has some rules. I'll just denote usually assignments for in the four-way logic by W's, right? So it's just W. Now, okay, so what should we do here? We have the function corresponding to TP. I can't use TP because TP is defined over 2-value logic, and now we are using 4-value logic, so I don't want to use the very same name for this function. So for TP is phi p, and this phi p is just 4 to z, 4 to z. So basically each variable gets a value from the 4 values, from the 4 possible values, and that will be an assignment, and this will be transformed into another assignment. But again, we will assign intervals for each value. Now, 4 to z, 4 to the z, okay, defined as before. So basically, if I'm just transforming variable assignment, and I just want to check the new value of a variable variable r, then I have to collect all the clauses which have r on the right hand side within the program, right? So this is just the collection of all the clauses which have this r on the right hand side, similar as before, and I just have to take a large disjunction, supremo of these values. This time they will be intervals. And how should I compute it? Well, I have to just compute the variables values, which are intervals here, and then for the negated variables I have to negate their interval as well. We will see an example for this because it can be hard in the first time if you've never seen logic programs and clauses and stuff like that. But basically this is what we should do. Just evaluate the left hand side of all the clauses according to the rules we've just invented for computing with intervals, and then you just take the supremum of these body values, and that will be the new value of their common head. So let's see this on an example. So, example. So, for both the logic program and how to apply this function phi. So again, it's allowed to use an empty left-hand side. And again, an empty conjunction is just the infimum of the empty set in the truth ordering poset. So this will be true. Okay. And then I can use, say, P and Q to R. Why not? And I can also say that P implies Q, and I can also say that not P implies Q. And I can also say that, say, S implies R. Why not? So we have here 4 variables, P, Q, R, and S, and we have one single rule which has a negation. This guy has a negation there. Now let's try. So first we will just assign the unknown value P, Q, R, and S to each of these variables. Why the unknown you will see, but this is how we roll. Now P, Q, R, and S. We have these values set to unknown originally, and then we just try to compute the phi P of this particular assignment. Now okay, let's just compute the values for each of these variables. What should be the value for P? Now for the value of P, I have to collect all the clauses having P as head. That's the only clause here, having P as head. Okay. So then I have to evaluate its body. Okay, so it's an empty conjunction. Good. An empty conjunction will have the value of, we have the true value. Okay. And then we have to take the supremum of this single value, so this will be true. Yeah, that's great. Now for the new value of Q, so I have to collect all the clauses having Q on the right hand side, so there are 2 such clauses right now, and evaluate the left hand side according to my current variable assignment. So the value of P is unknown at this point, and the value of not P is also unknown at this point. So I just evaluated both bodies having Q on the right hand side, and I have to take the supremum of these 2 values, where this is exactly 1 value at this point. So the supremum of unknown and unknown will be unknown. So note that although if P entails Q and not P entails Q as well, then in the classical logic we can deduce that Q is true, but not here. So here, well, unknown twice won't entail true, it just entails unknown as well. Now for R I have also 2 rules, this guy and that guy. But P and Q is at this point, this is unknown and unknown, and it's unknown. S is also unknown, so I will get the value of unknown here. Now for S, there is absolutely no absolutely no clause with the right hand side being S. That means that I have to compute the value of an empty disjunction, and an empty disjunction is just false. So if there is absolutely nothing which would entail S, then S will be set to false. Now that's okay, that's a thing. and I can just iterate this once again. And if you do the computations, then you get that this P is again true, because this is the only clause having P on the right hand side, and its left hand side is true. Again, since I have no S on the right hand sides, then it will be the new value of this S will be the supreme of the empty set, which is false. Now for Q, this time I have the P to Q, and the P to Q here the body evaluated true. Here I have the not P to Q, not P is false, so the body evaluates false. Okay, I just evaluated both of the clauses having Q as head, and I just have to take the supremum of true and false, the disjunction of true and false, which will be true. So I eventually got this in the second step. Now for R, I have a P and Q which is true and unknown. Well, true and unknown is unknown. You can check the infime operator in the truth ordering. So I have unknown on one of the clauses, and S is false at this point. So I have to take the supremum of unknown and false, which is unknown according to the truth ordering, because false is the least element of the truth ordering, so that's still unknown. And then in the next step I'm just iterating, and I will get that this is still true, this is still true, this is still false, and for R I will get here false, but here for P and Q I will get true and true, which is true. And now I will have to take the supremum of true and false, which will be true. Okay, and this will be mapped to itself, so this is a fixed point. Actually, it seems that we just converged. Yeah. Now again, the thing is, and it can be proved with pretty much the same way as before, again, an assignment W, but this time W is a 4-valued assignment, just like the previous ones, is a model of the program if and only if we transform the assignment by the phi function. Phi p of W is smaller than or equal to W according to the truth ordering. Yeah. Why? Because implications are satisfied this way. So if the implications left hand side is at most as true as it right hand side, and we need this for all the clauses, then it makes it quite easy to compute this, and it can just be computed the very same way, because we haven't used actually anything about the classical logic's properties, only the part where we evaluated the implications, which should be evaluated the very same way as before. Now, okay, so we have this function phi p of W, and we can see that this is something which either converges to something or not. We can check another example, like the not P and not Q, not P and not Q entailing R, not Q and not R entailing P, and not P and not R entailing Q. Now if you do the very same thing, P, Q and R start from the unknown values, and then just make the iteration for one step, then what will you get? The negation of unknown is still unknown, this is still unknown, and the conjunction of two unknowns is still unknown, and so you just have to set the new value of R to unknown, and the new value of Q and the new value of P to unknown as well. So basically the unknown value is already a fixed point, which means it's a prefixed point as well for this function phi p, which means that here we get a model which is the unknown. And actually it might make sense, might make more sense to say that, well, if you want to construct a model, then I don't know anything about the value of the variables, then just picking one of those minimal models. So this is a model, and well, if you just set, say, p to true, say, so if you just set p to true, then you will get something which is true, false, false. This is also a model, because well, true, true, false, that's also a model, and so on. So there are many models of this particular problems, but this guy here, this unknown is also one of those minimal models according to the truth ordering, because if you use at least one classical variable, then well, so this 0, 1 is well more true than the false value and less true than the true value, but you cannot use 3 false values. So if you just use at least one value of true, then that won't be a strictly smaller assignment than the unknown. Now anyways, this will be one of those minimal assignments, and there will be many other minimal assignments, but we will see it later whether it makes any sense to choose this as a minimal model of the original problem. I'd say in this case it makes sense, because you have absolutely no reason why to choose any other configuration of true and false. So it's safe to say that you don't know anything about these guys, because you can't really say that well, I don't know anything, but I know that it cannot happen that each of these values is a false. So it's not really possible in this framework. Now there is a problem with this, and I will just make a new slide to introduce the problem. So the problem is, also in the previous example we converged sort of to a solution in just a finite number of steps. It's not always the case, and it's not always the case that it's enough just to take a supremum like in the classical setting. So we have a problem here with this function phi. It's not continuous. What does it mean? So for example, if you just have the following program, nothing, the contraction of all things, implies p0, so this states that p0 is true. And p0 implies p1, and p1 implies p2, and p2 implies p3, and so on. So far it's not that complicated. You can see that you have to set all of these pi variables to true eventually, right? So it's because p0 has to be true, and then because of the second clause p1 also has to be true, and so on. So this is just basically an induction. And then you can introduce the not p0 implies q, not p1 implies q, the same q, no index, not p2 implies the very same q, not p3 implies the very same q, and so on. Yeah, you can actually get such a program from first order logic program consisting of 3 actual clauses, generalized clauses, so it's quite possible. Now, what happens? So if you just iterate this function p0, p1, p2, and so on, okay, p3, and so on, and we also have one single q at the end of this column. So originally we will have everything set to unknown. Then, applying this very first clause, we will get that the value of p0 has to be true, because there is a clause on which p0 occurs on the right hand side and whose left hand side evaluates to true under, well, any circumstances, so it's true. Now for the others, I cannot say anything right now, because every other body is evaluating to unknown, so it's unknown, 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 and unknown. But then in the next step, setting p0, because of this guy here, p0 to p1, I already know that p0 is true, and this is the largest element according to the truth ordering, so I will have to set p1 to true. Now for p2, for example, I'm still stuck at the unknown value, because in this iteration p1 is unknown, so p2 is unknown as well, and p3 is unknown as well. Now for q, the thing is not that complicated, so the negation of p0 is false at this point, but here we have unknown and unknown and unknown, and I have to take the supremum of these left hand side, because that's the definition of the function phi p. So just collect all those clauses having q on the right hand side, compute the value of the bodies, and take the supremum of this thing. And the supremum of this thing is just the supremum of false and unknown, and you can check that it will be unknown. So it's still unknown. And in the next step it will be true, 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 unknown, and unknown. In the next step it will be true, 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 and unknown. Well, I could say and so on. So at each step I will make one more variable, one more pi to be true. So if I just take it to the limit, sort of, and compute the supremum of this assignment, I will end up by something which sets all the pi's to true, supremum, 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 and the supremum of these unknown values is still unknown for the case of q, but this is not a model. So in the case of TP, it was enough just to take one supremum, and that gave me a solution. But if you just try to compute the next iteration after taking this supremum, then we have these values still set to true. But for q, now since each pi is true, then each not pi is false, and I have to compute right now the supremum of false, which is false. So after one more iteration, I will get the true, 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 true. So setting each pi to true and setting q to false. And after one more iteration, I will get this back. So this is a fixed point. So this is a prefixed point, unlike the previous one. So this will be a model of the program. This is actually the first element of this long sequence. It's longer than infinite if you just take it a bit less seriously. So it's a model. the first model we have. So it seems that we can compute a model of a program using some iteration, but right now the iteration will be longer. So it might happen that after taking the supremum, we still have to take some more steps. It's even possible that we have to take supremum once more and then take some steps, and again taking the supremum, and so on, and taking some steps. Now this is exactly because this function is not continuous, because the Tarski theorem says that if this function would be continuous, then taking one single supremum would be enough. So remember, the Tarski fixed point theorem stated that if you have a continuous function in complete partial order, then at least prefixed point exists, and you just have to take the supremum of this iteration sequence. But it doesn't hold here because this function is not continuous. But this function is monotone with respect to the precision ordering. That is something monotone. That is something we can show. So this means that if W is less precise than W prime, then the transformed variant of the W is also less precise than the transformed variant of W prime. So that's what P monotone means, and we will prove this aim. And our current aim is just this: show that it holds, so phi p is monotone. And there is also another fixed point theorem, the so-called Tarski-Kleene fixed point theorem. It says that any monotone function has a least prefixed point, which happens to be also a fixed point as well. So in complete partial order, so in spirit it's very similar to the Tarski fixed point theorem, but the Kleene fixed point theorem states also that it can be computed by an iteration sequence, but in this time it's not always sufficient to just iterate over the integers. So Kleene fixed point theorem: if f is a p2p function, monotone, and p is a CPO, complete partial order, then f has least prefixed point. A prefix point. And these two things together will give us the so-called Kripke-Kleene semantics of generalized logic programs, because, well, if we have these two, then it suffices just to compute the least prefixed point of the function phi p, and we will end up with some model of the program. Now there is some clash here, because phi p is monotone with respect to p, the precision ordering, and we want to end up by a prefixed point of phi according to the truth ordering, but we will solve this as well. But not in this video. So in the next video I will try to show that this function phi p is monotone, but for this I will have to change this function a little bit, and it will need some more mathematical background. So I think I'll stop here, and till then, bye bye.